Okay, guys. Now, we are going to look at this question. This is a buck regulator with input voltage 12 volts. And that's the switch here, and the switching frequency is 25 kilohertz. All right, we have our diode, then we have inductor here, and the peak-to-peak ripple current on the inductor is 0.8 amps. All right, and here we have our capacitor, and then the ripple voltage, okay, the peak-to-peak ripple voltage is 20 millivolts, right? And then the output voltage is 5 volts, and the load is 5 ohms. So with this case, the question is to calculate the duty cycle. That's number one. And number two is to calculate the inductance of this inductor, and also calculate the capacitance of this capacitor. Did you get it? All right, so what we are going to do is, let's start with the first one, the duty cycle. What do we say the duty cycle? We say duty cycle K is the same thing as what? VO over Vs. So K is VO over Vs. And the output voltage here is 5, and the input voltage is 12, right? So we'll have 5 over 12, which will give you 0.4167. So we'll have 0.4167. All right, that is a duty cycle. Then the next question is to calculate the inductance of the inductor. Now, how do we calculate that? We need to look for any equation that relates inductance with maybe voltage on the inductor. And the only equation that we know is that the voltage across inductor is the same thing as inductance by change. Okay, let's use that by di dt. That VL, the voltage across this inductor, is the same thing as saying VL is L di dt. That means we can write this like this: L delta I over delta T. Okay, did you get it? Now, that is your VL. So now what we are going to do is, let's look at the states, the different states of this buck converter or buck regulator. On state and off state, when this is on and when this switch is off. So that at the time the switch is on, I will only use this as T on. So that I have this as T on, then I have this as a voltage across the inductor, then I can use this with that, with the ripple current, to calculate the inductance. Did you get that? Okay, look at what I'm saying. If you switch, we are going back to our previous video. If you switch this on, when this is on, current flows like that. All right, so you only have this. You have that our Vs we take care of, or is the same thing as VL plus output voltage, like this. Right? So that VL will be the same as Vs minus VO. Okay? So that means here I know this now. VL is Vs minus VO, and I know my Vs to be 12, VO to be 5. And I said, okay, this is the same thing as L delta I over delta T. And this T, this equation is for time of on. Right? So this is T on. And this T on, what do we say is T on again? T on is KT, right? T on over period equals to duty cycle. So that T on is KT. All right, so that means I can write this now as Vs minus Vo equal L by delta I over Kt. That's all. So we can now make L the subject so that the inductance of the inductor L will now give you Kt into Vs minus Vo, okay, divided by delta I. That's all. We can now substitute our values. We have our K to be 0.467. So we have our Vs to be 12. We have our Vo to be 5. Then you divide that by the ripple current. And ripple current is given to you there as 0.8. Divide that by 0.8. Okay? So when you divide this, okay, then you get the value. You get the value. Oh, did I miss something? I missed something. I missed my T. All right? Okay, look. So I have K. I forgot T. So let's put our T there. Now, T. Is there any T there? What we have here is frequency. What's the relationship between frequency and period? Frequency is 1 over T, or T is 1 over frequency. So it means that I'm going to multiply this 1 over 25,000. So I have 1.6 times 10 to 1.63, 1.6345 times 10 to the power minus 4. Okay, in Henry. All right, so 1.6345, okay, which is 163.45 microhenry. All right, so now that's all about that. Then the next question is to calculate the capacitance of the capacitor. Now the next thing again, how do we calculate capacitance? Which equation are we going to use? And in the last video we didn't do anything like that. So the only thing that you need to know, all right, is that the current flowing through the capacitor, the current flowing through this capacitor into that capacitor is also because going up, discharging. It builds up and discharges to the load, right? So it means that the current flows like that at time of on, at time of off. So it discharges. At time of on, it goes up. This is our average value, right? Time of on, it goes on. Time of off, off. Okay? So, now, when the capacitor is charging, all right, when the capacitor is charging, all right, you are going to get the quantity of electricity. And our quantity of electricity during charging is the same thing as the capacitance times the voltage. Right? So that means if I say, okay, the change in quantity of electricity is the same thing as capacitance times change in voltage. And at time of on, for us to get the quantity of electricity, now we'll be looking at here, from here to there, which is supposed to be the whole of this and this, because this is your IC versus time, right? So by the time I get the area of this and the area of that. This is for the time of on, the whole of that. So that will give us the quantity of electricity. Okay? So, but I know that the area of this, remember that from here to somewhere here is your period. This is your period T. So by the time you have 1, 2, 3, 4, this is like from here to here alone is period over 4. Here, period over 4, over 4, over 4. So if I just want the period, the time for this time of on, because the quantity of electricity at during time of on, during charging, is the same thing as during discharging, right? All right, so we know that from here to here is T over 2. So now what I'm going to do is, let me rather just consider from here to here the whole of this, which is the same thing as saying considering this plus that, right? So now I will just use this section to get the quantity of electricity, right? So from here to here is period over 2. Why? Because this is period over 4 plus period over 4 plus period over 4 plus period over 4, which is period. So that means from here to here is period over 4. Here to here is period over 4, which is altogether period over 2. Okay, so I'm going to use this to now calculate. So what am I going to do? The quantity of electricity, okay, that we have there at this point is the area of this triangle. And area of triangle is half, okay, let's write it here, half base times height. That is for quantity of electricity for this triangle here. And that half base is the same as half times, what is the base? The base here from here to here is T over 2 times, what is the height from here to here, right? What's that height? Remember that from here to here is your delta I, your ripple current. So that from here to here, which is this to this, is ripple current divided by 2. So that is your height. And this is the quantity of electricity. So, and this is the same thing I'm now saying, C times delta V. See, now I have a nice equation that I can easily calculate C, because I know delta V is given to me somewhere, and I have delta I is given to me somewhere. The period is also given, and this is constant, so we can easily calculate C. So which means that the capacitor C can be written as, just make C the subject formula. All right, let's see what we have here. So will be T by delta I divided by this times this times this, that is 8 times delta V. It's okay, right? Okay, so we have that. So we have C equals T by delta T. What is it? T by delta I, sorry. By delta I. T by delta I. Divided by 8 by, multiply by that. Okay, it's okay. Now, what is our period? That's a frequency, switching frequency there is 25. So our period is 1 over 2,500 times delta I is given to us there as 0.8 divided by 8 times delta V, which is given to you as 20 times 10 to the power minus 3. So we have 2 raised to the power 2 times 10 to the power minus 4. Okay, farad, isn't it? Which you can write as 200 times 10 to the power minus 6 farad, or 200 microfarad as the capacitance of that capacitor. Did you get that? All right. Okay. Now, let's assume that you are asked to calculate the critical value of the inductance. Okay? The critical value of this inductor. Let's say you are asked to calculate critical value. All right, and also the critical value of C, L and C. if you are asked to calculate the critical value, remember, by the time you'll be doing your simulation, you will see that the value of the inductance will affect the ripple. All right, so there's a value of inductance you put there, then you will just get nothing. You'll see a very big ripple. So there must be a critical value of your inductance. So now the critical value of inductance, just from the same equation that we have, that we said Vs minus Vo equals L delta I over Kt. We are looking for critical value of that. Now, just note this, that at critical value, right, delta I will be twice of the output current. And at critical value, if you want to get critical value for capacitors also, the voltage across here, delta V will also be the same thing as twice of the output voltage. Did you get that? All right, so let's start with this first. As I said before, so for you to get critical value, this delta I will change it to twice of IO. So that Vs minus Vo equals L critical multiplied by twice of IO divided by Kt. So that if you just do the same thing we did here, L critical will now give you Kt into Vs minus Vo all over 2 times IO, like that. Did you get that? So from here, you now have our K. Our K is 0.467, and our T is 1 over 25,000, and the Vs minus Vo, which is 12 minus 5. Okay, 12 minus 5 is 7, right? 7, all right. Now divide by 2 times IO. All right, you don't check your IO. Is there any IO there? I don't see any IO there. So you must look for a way to calculate your IO. The resistance is given, VO is given. So you can calculate IO. V is equals to IR, right? So you can easily calculate your IO, all right? So let's have our IO here. It's the same thing as, remember, V is IR, right? So I is VO over R, which is 5 divided by 5, giving you 1. Okay, so our IO here is 1. All right, so you can evaluate that. So let's get the answer there. So we have 6. We have that to be 6.538 times 10 to the power minus 5 Henry. Okay, which is like 65.38 micro Henry. Okay, that is 65.38 times 10 to the power minus 6, 65 micro Henry. Okay, did you get that? So that's our critical value of the inductance. While the normal, from that equation, we use this, okay, to get all those parameters. But if you are changing the value of the inductance to see the performance, how the system performs, right? That is a critical value. As you are changing, as you are reducing, this is about 163, okay, micro Henry, and then you are reducing it. You want that to be smoother, to be better. It should not go less than that, 65.38. Okay. Now we can do the same thing to calculate the value, the critical value of the capacitor. All right. What do you do? Let's see where we can put it. Remember? All right. So here, I said critical value of the capacitor. C critical, delta V will be twice of the output voltage. So here that we write the capacitor, you just write capacitor critical value is T times delta I divided by 8. Here is just times twice of VO, 2VO. That's all. So just put the values that you have there. So we have T is 1 over 25,000. All right, multiplied by delta I is 0.8. Divided by 8 times twice of VO. And our VO is 5. So 2 times 5. So we have that to be 4 times 10 to the power minus 7. Okay, farad. Did you get it? So, which is how many microfarad is that? That should be 0.4 microfarad. Right? So 0.4 microfarad will be the critical value of this of the capacitor. All right? Okay? Thank you.